Good day, class! I am Christiana Yap, your teacher for your specialized subject for this semester. So we have finished our pre-calculus lessons last semester, and for this semester we are having our basic calculus lessons. First, we need to understand what is calculus. Calculus is the study of how things change. It provides a way for us to construct relatively simple quantitative models of change and how to deduce their consequences. Calculus, by giving professionals and you the ability to create and control systems, gives us extraordinary power over the material world. But why is there a need for us to study calculus? The purpose of studying calculus is to simply introduce your mind to the scientific method of analysis. First is to introduce you to the basic concepts of math used to study almost any type of changing phenomena. Second, studying calculus helps you develop invaluable scientific sense and practical engineering problem-solving skills in you. The development of calculus and its application to science and engineering is probably the most significant factor in the development of modern science beyond where it was in the days of Archimedes. To assist you in understanding calculus, how it is used in our lives, please listen to this short video tutorial. Let us start understanding the concept of limits using tables and graphs. So everyone has their own limitation. Knowing your own limit helps you to understand why some things are favorable to you and some are not. In this branch of mathematics called calculus, limit is one of the most important lessons that you need to understand because it plays a vital role in the application of differentiation towards a function. It is essential to mathematical analysis and is used to define continuity, derivatives, as well as integrals, which we will discuss later. So it is also used to understand the behavior of functions as to what value it approaches to when given a certain data. For example, when designing the engine of a new car, an engineer may model the gasoline through the car's engine with small intervals called a mesh. Since the geometry of the engine is too complicated to get exactly with simple functions, these approximations always use limits. Another scenario is when you are traveling with your own vehicle and you find many speed limit signs along the way. This is also an example of limits used every day in our lives without us knowing. The limit, to be denoted by L of a function f of x, is a value that approaches as the value of x approaches a certain value called c. This is written in symbols as follows and is read as the limit of f of x as x approaches c is L. So in evaluating the given limit, we will use a table graph to keep track of the effect that the approach of x towards c will have on f of x. So, one-sided limit is a value L as the x value gets closer and closer to a certain value c from one side only, either from the left side or from the right side. So in symbols, we write this as. So always remember that if the limit value from the left side is not equal to the limit value from the right, then the limit does not exist, or D and E. In symbols, we write this as. So now, let us answer an example found in our module. Look at number 3, letter A. The first thing we need to do is to create two separate tables with two columns and rows. Label the upper left of the two tables as x, while the upper right should be f of x. Since x approaches 3, let us now create at least 6 values lesser than 3 but close to it, while the other table should have 6 values greater than 3 but close to it. And then start replacing our x values to the given equation. The 6 values of each table should have the same value or approximated value. In this solution, the two 6th values have the same approximated value, which is 10. So we can say that limit of 10 over x minus 2 as x approaches to 3 is equals to 10. So lesson 1 showed us how limits can be determined using either a table of values or a graph of a function. However, this can be a very tiring work. Thus, in this lesson, we will be using the easier alternative, which is by using limit theorems. Here are the 8 different theorems that you can apply in various situations to solve for the limit of a function. So theorem number 1 states that the limit of a constant is itself. So if limit of k as x approaches c, then it is equal to k. For example, limit of 1000 as x approaches c, then the answer is 1000. So the next theorem states that the limit of x as x approaches c is equal to c. So if limit of x as x approaches 1000, then the answer would be 1000. The next theorem is called the constant multiple theorem. It states that the limit of a multiple of a function is simply the multiple of the limit of the function. To better understand this, here is an example. Limit of 3x as x approaches 3.14. Since x approaches 3.14, substitute 3.14 to the x of 3x, thus it will be 3 times 3.14 and it will equate to 9.42. The next theorem is called the addition theorem, which states that if the limit of a sum or difference of a function is a sum or difference of the limits of the individual functions. For example, limit of f of x as x approaches c is 4, and the limit of g of x as x approaches c is -5. We will have two answers for the sum and the difference. For the sum, the answer will be 4 plus -5 equals -1, while the difference would be 4 minus -5 equals 9. The fifth theorem is called the multiplication theorem, which is very similar to the previous theorem, but the difference is the operation involved. In this case, we will be using multiplication. So the limit of a product of a function is equal to the product of their limits. For example, limit of f of x as x approaches c is 4, and the limit of g of x as x approaches c is -5. So we will multiply both limits and then simplify, like 4 times -5 equals -20. The sixth theorem is called the division theorem. It states that the limit of a quotient of a function is equal to the quotient of the limits of the functions, as long as the denominator is not equal to 0. Because if it is, then the answer would be D and E, or does not exist. For example, limit of f of x as x approaches c is 4, and the limit of g of x as x approaches c is -5. You divide both limits and it will be equal to -4/5. So the seventh theorem is called the power theorem. It states that the limit of an integer power p of a function is just the power of the limit of the function. So for example, limit of x squared as x approaches 2 is equal to 4, because since the exponent is 2, so it will be 2 squared equals 4. So the last theorem is called the radical or root theorem. It states that if n is a positive integer, the limit of the nth root of a function is just the nth root of the limit of the function, provided the nth root of the limit of a number is a real number. So if limit of f of x as x approaches 2 is 4, then the square root of limit of f of x as x approaches c is equals to square root of 4, and it will be equal to 2. While limit of f of x as x approaches 2 is -4, the answer would be D and E, because square root of -4 is 2i, and 2i is not a real number. There are instances where all theorems will be applied in just one equation. Now let us have a quick overview on our next lesson, which is infinite limits, exponential, logarithmic, and trigonometric functions. In this given graph, we can see that the function is not defined at x equals to 0, but you can still check the behavior of the function as x approaches 0 intuitively. So as x approaches 0 from the left, the value of the function increases without bound. When this happens, we can say that the limit of f of x as x approaches 0 from the left is positive infinity. In symbols, it will be, again, as x approaches 0 from the right, the value of the function increases without bound. So we can say that the limit of f of x as x approaches 0 from the right is positive infinity. In symbols, since both of them are equal to positive infinity, we can conclude that the limit of f of x as x approaches to 0 is positive infinity. However, in this graph, as x approaches 0 from the left, the value of the function decreases without bound. So we say that the limit of f of x as x approaches 0 from the left is negative infinity. And we put it into symbols as x approaches 0 from the right, the value of the function decreases without bound. So we say that the limit of f of x as x approaches 0 from the right is negative infinity. And since both are equal to negative infinity, we can conclude that limit of f of x as x approaches 0 is negative infinity. Flowing water, long-winding roads, and waiting for forever are just examples of uninterrupted actions or continuity. There are times wherein some actions were meant to be disjointed or disconnected. Somehow, the concept of continuity is also present in calculus, and it will be discussed to you in details as you go on with this tutorial. So what does continuity on a point exactly mean? Intuitively, a function is continuous at a particular point if there is no break in its graph at that point. But how can we really know if a function is continuous or not? There are actually two possible ways in determining if the function is continuous. The first one, and the easiest one, is through a graph. The easy method to test for the continuity of a function is to examine whether a pen can trace the graph of a function without lifting a pen from the paper. For example, in this graph, we need to determine if function h of x is continuous at x equals to 2. The graph is continuous at x equals to 2 because we are able to trace the graph from the left side of the number going to the right side without lifting one's pen. The second way is through satisfying these three conditions. The first condition is that f of c must exist, meaning not d and e. The second condition, limit of f of x as x approaches c exists, meaning not d and e. The third condition states that f of c is equals to limit of f of x as x approaches c. If the first two conditions are both d and e, applying the third condition would be wrong logic. D and E is non-existing and therefore we cannot provide an answer. For example, determine if f of x equals x cubed plus x squared minus 2 is continuous or not at x equals to 1. So we should check if the three conditions have been satisfied. The first condition is satisfied because if x equals to 1, then f times 1 is equals to 0. The second condition is also satisfied because limit of f of x will equate to limit of x cubed plus x squared minus 2 as x approaches to 1. And then substitute 1 to the x, so the result will be limit of 1 cubed plus 1 squared minus 2 as x approaches to 1 is equals to 0. Since the first two conditions are equal to one another, we can say that the function is continuous at x equals to 1. In real-life scenarios, continuous functions, believe it or not, are all sorts of useful. For one thing, they're the secret behind digital recording, including CDs and DVDs. Everything from ocean tides to stock prices can be modeled by differential equations, and one cannot solve any differential equations without studying continuous functions. So let us now proceed to derivatives. So derivative is an instantaneous rate of change. It tells you how quickly the relationship between your input x and output y is changing at any exact point in time. And derivatives, which is a mathematical model of change and has amazing prediction powers, is extremely useful in our everyday life. As a STEM professional, specifically in the field of biology and chemistry, derivatives are used to model population growth, ecosystems, spread of diseases, and various phenomena. One use of derivatives in chemistry is when you want to find the concentration of an element in a product. Derivatives is also used to calculate the rate of reaction and compressibility in chemistry. If you are an entrepreneur and you want to see if your profit for a particular month has either dropped or increased, you can definitely use derivatives. You can do this by using graphs. That's the concept of derivatives is used. There are two ways in finding the derivative of a function. The first one is by using the delta method and slope of a tangent line at a given point. However, using this method at a limited time is impossible to finish. So, the derivative rules were created to find the derivative of a function in a more convenient way. Although all these rules discussed were derived from the delta method. Alright, I know some of you now are probably sleeping already, but hey, good news everyone. We are now in our final topic for basic calculus, and that is the integral calculus. So first, let us define what an integral calculus is. So integral calculus is the branch of calculus where we study about integrals and their properties. Integration is a very important concept, which is the inverse process of differentiation. That is why it is usually called as anti-differentiation. So let us now know its importance and how it is very vital in our everyday life. So integral calculus is important due to various real-life cases and the handy tool it provides for various real-life application. It is used in finance to price bonds and options, and is also used by credit card companies to set the due on credit cards. The technique of integration is important, especially in the medical and engineering field. In the field of medicine, integration helps in studying the spread of infectious diseases like COVID-19. It can be used to determine how far and fast a disease is spreading, where it may have originated from, and how to best treat it. It also helps to determine the rate of a chemical reaction and to determine some necessary information of radioactive decay reaction. Integral calculus is also used by architect engineers to determine the need for material for the construction of a building. With all that said, from the lessons I have discussed and the importance of calculus I have partaken to you, you can already visualize and see the flow of basic calculus in the lives of the people, not only for those who are studying it, and how it has helped humankind to achieve things that was considered impossible, how it has given us the knowledge that we need for a future endeavors. It has been the queen of mathematics and has been among the most important gifts that the mathematical world has given to us. Though it is very complex to understand, remember that nothing worthy can be found in the easiest paths.